Okay, so we're going to be talking about classifying types of chemical reactions on page 6 and 7 in your packet. But before you write anything down, let me give you a quick synopsis of what we're doing. Because we're classifying types of reactions, we're going to be looking at what types of substances are in those reactions. And when you classify them, and I don't mean ionic or covalent, I just mean as the basic level of element versus compound, you're going to see that those substances change in the reaction. And if you see elements turn into compounds, that's going to be one type of reaction. Compounds turning into other compounds is a different type of reaction. And that's all that we need in order to be able to classify our types, is classifying the types of substances. So let me real quick recap with you. You can write this down if you need it, otherwise just skip it for right now. Compounds are two different elements together. It means I have two or more different symbols from the periodic table. Elements is only one type of atom, one symbol from the periodic table. That does include my diatomic elements, like chlorine. That's still just one symbol from the periodic table, so that is still an element. Now, another thing before you start writing anything down, this is a list of the 5 different types of chemical reactions. You need to know these, even if you don't write them down right now. You're going to see these names throughout our notes today, but these are your 5 choices. This is kind of your word bank for the quiz, even though when you're classifying reactions on the quiz next week, you will not have a word bank. So you do need to memorize these names and be able to come up with them. And make sure you know these names, not just the nicknames I'm about to tell you, because there are some fun nicknames for these reactions that help you see how the elements relate to each other, kind of like a real person relates to another in a relationship. So our first reaction is a synthesis reaction. And just like photosynthesis is making food from sunlight, synthesis is things combining together to make something new. And if I were to make an analogy to relationships, this is kind of like a marriage. You'll see in this general equation over here that I have 2 separate things, A and X, coming together to make AX. And that's the key to be a synthesis reaction, is we have to form one compound as a product. This purple writing and anything else that you see as purple is something that you absolutely have to write down. No choice about it. This is required information. And that is the only way to tell if something is a synthesis reaction, is if it forms one compound. Now, you'll notice in my Mg plus O2 example, I am forming MgO. That is one compound there. Where it might get a little bit confusing is if you balance this, you'll see those 2 coefficients there. And that 2 in front of the MgO might make you think that there's more than one compound there. But really, you're just making one compound, MgO. It's just that you're making twice as much of it with that 2 there. So that doesn't change the fact that this is a synthesis reaction. Balancing shouldn't change anything. And you don't even really have to change it into its formula form. Even with a word equation, seeing lithium plus oxygen making lithium oxide, I'm making one thing, it's still synthesis. Now, that last example, I am going to change into formulas just to kind of reinforce and show you that this is 2 compounds coming together to make another compound. It's weird and different because it's not elements, it's compounds coming together, but as long as I have that one compound as my product, then I am still a synthesis reaction. Decomposition reactions are the opposite, just like decomposers break things down instead of building them up. Decomposition is the opposite of our synthesis, our marriage, so that's why I call it the divorce. In my general equation, you'll see this is the exact opposite of my synthesis reaction. I have one thing breaking up into 2 things, and that's what we need to be looking for, is one compound as our reactant. If I only have one group before the reaction, there's nothing else for it to react with, it must be reacting with itself and breaking down. Just like in synthesis, it could break down into 2 elements, kind of like the examples that we see here, where I make Mg and O2 separate again, or it could break down into 2 compounds or an element in a compound. It doesn't matter what it breaks down into as long as it has one compound as our reactant. Now, you'll notice each of these reactions look like they have 2 things here. I have some heat added in or some electrical current, and you won't always see those there, but decomposition does require energy, and so you might see that written into that equation, but You might also not see it there. So don't just look for that energy. But remember, energy isn't really a real thing. It's not a substance. It is just energy. So that does not count as a compound or an element, and thus MgO is still alone on that left-hand side of the reaction. So those are my simplest two. They also tend to be the shortest because one side of the reaction only has one thing there. Makes them pretty easy to balance. So you might go looking for these synthesis and decomposition reactions to make them easy balance problems. Now, they start to get a little bit more complicated as we get to our next example, the single replacement, but it's really not too bad still. I'm going to go ahead and tell you the analogy that we use for single replacement reactions is the home wrecker, and you'll understand that a little bit better in a second. But in a home wrecker single replacement reaction, we have to have one single element and one group compound on each side. So I need to have an element and a compound on my reactant side, and that has to make an element and a compound on the product side. I'm just using E and C to represent element and compound. They're not really the same things. And let's take a closer look at this general equation over here to kind of see what's happening here and why I'm calling this a home wrecker reaction. I'm actually going to simplify that reaction a little bit more and take out the words element and compound for a second. If you look at this, you will notice my element and compound on each side. A is my element here, Bx is my compound. And then on my product side, B is my element, and Ax is my compound. So even though I have the same types of substances, they are different elements before and after the reaction. And what's actually happening here is that A is coming in and breaking up Bx. And A just didn't want to be single anymore. So A is now getting into this compound, and he kicked out B from that compound. And so now B is all on its lonesome here. So we have to have an element and a compound before the reaction, someone single and someone in a group. And then that single element is going to come in and break up the group. And now it's part of the compound and someone else is single. So to be single replacement reaction, we do have to have someone single and someone in a group on each side. Now, we have another little kind of caveat here, and I'm not going to go into too much detail, or I'm going to try not to. But the single element is always going to switch and replace the element with the same charge. So there's kind of two different types of single replacement reactions, but you don't really have to worry about them too much. It'll make a little bit more sense later when we go into more detail on these, because we will. But if we imagine that single element is a halogen, why? Halogens like to become negative. So as Y comes over here into this compound, it's not going to react with something else that's negative. It's going to kick out the other negative thing. In this case, that's the X, and get with the positive thing. And positives are always first. So if that halogen likes to be negative, and it's going to come over and react with the positive part of the compound, and that's why we ended up with By here. You'll notice on the next side of the page, we're kind of continuing with our single replacement stuff, but we're talking about if that single element is a metal, and metals like to be positive. So let's imagine this single this single A in this circumstance is positive. When it comes over to that Bx, it's going to kick out the positive part of that reaction, of that compound, and get with that negative part. So now A is coming in and reacting and getting with X instead of getting with B. So what I said previously was that the single element will always switch with the same charge. We'll worry about that more later. And just like with these halogens that I mentioned, halogens do tend to be diatomics. And so even though we see that 2 there, this is still an element reacting with a compound. And so this is single replacement. Now, After we're done with single replacement and we see those general equations there, we get to double replacement reactions. And double replacement reactions kind of remind me of that TV show, The Wife Swap. I don't know if you've ever seen that. It's a few years old. But they took one mom or wife out of one family and switched it with another mom, wife from another family. And in order to do that, they had to have two groups of people. So just like that, my double replacement reactions have to have two compounds on each side. Now that doesn't mean that it's not changing. If you look closer at this general equation here, AX is a compound, BY is also a compound. But after this reaction happens, I still have two compounds, but now A is with Y and B is with X. So I have two compounds on each side, but they are different compounds. Just like our single replacement reactions, our elements are going to switch and replace with the element in that other compound that has a similar charge. Really, when it comes down to it, what you're going to notice is that in a compound, whichever element is at the beginning is still going to be at the beginning of its new compound. Even when A switches up and it's not with X anymore, it's still going to have that same positive charge, and so it's still going to be at the beginning of our compound. So, two compounds on each side, and they just switch places. The only other thing we want to know about double replacement reactions, and go ahead and fix this for me because this will make a lot more sense. Look at that NaNO3. That has a lowercase o on your paper. Go ahead and make that capital for me. But the thing that I wanted to point out is that polyatomics move together. Just like they have a set group charge, when my compound breaks up here, Ag is my positive part, and that nitrate is the negative part. And that entire part is going to move and come over here. And when Na and Cl break up into their positive and negative parts, nitrate is going to get with the positive part. And I'm going to have a positive and a negative here, and then a positive and a negative there. So they always move to be with the opposite charge, and those polyatomic groups will move together. So that is almost all of our reactions. The last reaction is a combustion reaction, and there's no real fun relationship analogy for this one, but hopefully you understand that combustion means fire. My favorite type of reaction. Now, these reactions are going to have very similar elements in them because every fire needs the same basic ingredients. We need something to light on fire, our fuel. We need oxygen, and we need an ignition source, some sort of energy. And if you look at our general equation here, you'll see that exact thing. Hydrocarbon is the fancy word for fuel because most fuels do contain a combination, some ratio of hydrogens and carbons. They might also have some oxygens in there, but as long as we have something with hydrogen and carbon, that's going to be our fuel. Then I have to have oxygen, and that's always going to be O2. It's never going to look anything different. And what you might not know about burning things and combustion reactions is we always make the same products. And you might just see that as soot, or heat, or light, and you will have energy coming out. But we make the same two substances, CO2 and H2O. So really, if I were to make an always statement here, it would look pretty much like that general equation. We are always going to see some combination of X and Y, or of C and H, and I just put X and Y there to hold that place for however many I have, added to oxygen, making CO2 and H2O. Now, it doesn't matter what order they're written in. I could have that CO2 and H2O flipped, make H2O and CO2. As long as I'm making those same two things, it doesn't matter what order I write them in. I could also flip around the order of those reactants and have my oxygen plus my hydrocarbon instead of carbon and hydrogen plus oxygen. So none of this order matters. As long as I've got those same ingredients, it's going to react. So I'm going to leave that way. These combustion reactions can be a little bit trickier sometimes to balance, but once you know it's a combustion reaction, you can pull that tool out of your tool belt and treat it that way and understand that they're kind of all tricky in the same way. So go ahead and maybe try and balance some of these so that if you have any questions about them and need some help, then I can help you when you get back to class. So, that's all of our reaction types. Just in summary, my synthesis reaction was our marriage, where two things come together to make one compound. Decomposition is the opposite. One thing breaks down into multiple things. Could be 2 or 3 or 4 even. Single replacement, we got a single element replacing part of a compound, making a new single element and a new compound. Double replacement is 2 compounds on each side, but they switch partners. And combustion is fire, so we have to have the same old ingredients for fire and the same old products from fire every single time. So, only a few minutes shorter than Mrs. Mahoney's, but I do feel like I was a little bit more concise and hopefully comprehensible. So, give me your feedback when you see me in class next time. Thanks.